Hello, everyone. Welcome back. I'm happy to have you back. We are still on strike, so I'm recording this lecture. Please enjoy. Today, we are going to talk about z-scores. On Tuesday, or last lecture, whenever you're watching this, I introduced the concept that using the standard deviation and other measures of variance, we were able to quantify how common or how uncommon, in other words, how typical or rare a score is in a data set, whether it's unusually tall or short, unusually high or low levels of depression, unusually high or low numbers of hallucinations, whatever it is. That's what we're going to go into today. How exactly we quantify how typical or unusual, or how likely or unlikely something is. And we do that with something called z-scores. So far, what we've covered on week one, we talked about measures of central tendency, including the mean, the median, and the mode. And then last time, we talked about measures of spread, which are central tendency describes where a distribution of scores is centered. So where, say, for the mode, where the most scores are, the mean, where the average score is, and the median, where the middle of the set of scores are when they're sorted. Then we talked about measures of spread, in other words, how wide or narrow the distribution is. Are all the scores clustered around your measure of central tendency, whatever it is, or are they all spread out and some of them are very far from that measure of central tendency? And we talked about three types. First, the range, which is just the highest score minus the lowest score. And we're not really going to talk about that for the rest of the semester. It's the one that's most typically used outside of statistics, but we don't commonly use it in statistics. We also talked about the variance and the standard deviation. These are, well, I'll start with the standard deviation. The standard deviation is, on average, how far is a score from the mean. So, how far is the typical score from the mean? Within one standard deviation of the mean, roughly 69%, rounding up a little bit, of scores in any given data set are within one standard deviation of the mean. The variance is just the squared standard deviation. It's something that you calculate on your way to calculating the standard deviation. So yeah, we know how to determine where the most, say, typical score in a distribution of scores is, or in a set of scores is, and then how to describe how close or far away scores typically are from that typical score. I guess you could say how typical of the scores is that typical score. I don't know. Anyway, here's our lovely statistics iceberg. These are the two things that we're going to be talking about today, and actually the z-score is on this iceberg, but it's way towards the bottom. That's not because it's a particularly difficult concept compared to the other ones on this iceberg. It's mostly just that, for various reasons that we'll get into later, we don't really get to use z-scores terribly often. And that's why it's that far down. But we're talking about them today because it's a great setup for where we're going this semester. So yeah, there's a couple ways you can use z-scores, and one of them is this. You can use z-scores to compare scores from different distributions. And that sounds really abstract, so I'm going to use a bit more of a concrete example to convey what I mean. Let's say we've got this student, Dave, generic student Dave. Dave gets a 50 out of 100 on his stats midterm and a 50 out of 100 on his calc exam. We want to know if he did equally well relative to his classmates on these two exams. So in both cases, he got a 50 out of 100, which isn't necessarily great, but as you probably know, there are some classes that are easy A's, and getting a 50 in that class means you probably did really, really bad on that exam. And then there are what I believe are still referred to as weed out classes, where, a lot of people fail, and in that case, getting a 50 on that exam might be doing really, really well. In other words, we're talking about how he did on this exam relative to his classmates, or you could also think of it as relative to the difficulty of the exam. So the same score on two different exams might not necessarily reflect the same level of performance. A 50 on one exam might be very good, a 50 on another exam might be very bad, depending on the difficulty of the exam. But how can we compare this? It's exactly the same score, so if we just look at the scores, that's not really going to tell us if he did better on one exam than another. So let's look at this. This is our example of what this might look like. So this red line represents Dave's score on these two exams. Now, the solid line distribution on the left that says stats, that's average scores on the stats exam. The mean score on the stats exam that he took was 40. On the right, we have the calc exam. This distribution on the right represents the calc exam, and the average score on the calc exam was 60. Both of these distributions have the same standard deviation, so you could say there was the same amount of variety in scores on both exams. Now, even though he got the same score out of the same number of points, so he got the same percentage grade on both exams, he's 10 points above the mean for the stats exam and 10 points below the mean for the calc exam. And that's essentially what the z-score is going to be doing. It's going to be creating a number that says, here is how Dave did relative to average performance in the class. He did above average or he did below average. Because your grade on the exam only means it means something, but it's best interpreted, I'd say, relative to the other people who took the exam if you want to know how well you did relative to your classmates, right? So we're coming up with a score that tells us, yeah, we'll take that 50 and say, oh, he did above average in stats and he did below average in calc. So that's pretty easy, and honestly, we could just do that by eyeballing this and saying, oh, well, he's above the mean for stats and below the mean for calc, so he did better in stats than he did in calc relative to his classmates. And that's pretty easy. But things get a little more complicated when you have the same mean but different standard deviations. So here's another example. Another exam too. In this case, both the stats and the calc exam had a mean of 40. Dave still scored 50 on both. But the trick is, now stats and calc have different standard deviations. For the stats exam, we have a very low standard deviation. There's relatively little variability. Almost everybody is scoring around 40. We've got a few people who are maybe scoring around 25, a few people who are scoring maybe around 55, but they're all pretty close around 40. Calc, on the other hand, the average is 40, but we had some people who were getting zeros on that exam, and we had some that were getting 90s. There's a much wider variety of scores in the calc exam than the stats exam. Because there's such little variety in stats, with most people scoring very close to 40, Dave is performing better than 98% of his classmates on the stats exam. But because there's such a wide spread of scores in calc, Dave is only performing better than 69% of the class on the calc exam. So even though he got the same score on both exams, and both exams had the same average, he scored above average on both of them, he scored better than more of his classmates in stats than in calc because of that standard deviation. And that gets a little harder to eyeball, especially if it's not such a stark difference in standard deviation like this one. This is pretty obvious. You can just look at it and say, oh, yeah, there's more students to the right of Dave in calc than there are in stats. And you can kind of eyeball it, but differences in standard deviation aren't always this big, which is why we use z-scores, so that we don't have to try and eyeball it. Oh yeah, by the way, in this case, the standard deviation for stats was 5, for calculus it was 20. And that's what made the difference in his performance. So we need something that can tell us, did Dave score above or below the mean? And how far above or below the mean did he score relative to his classmates? In other words, we're taking into account both the mean of the distribution, Dave's score on that distribution, and the variability of the distribution. We're taking all three of those things into account to create a single score saying how far away from the mean was he and in which direction. Which leads us to something called standard scores. Now, what I've been working with so far that I've been telling you about are raw scores. We call them raw scores because you can think of it like statistics is cooking. Raw scores or raw data is data that we haven't done anything to. We haven't done any math to it yet. That's why we call them raw. I don't know if that's why we call them raw scores, but we call them raw scores when we haven't done anything to them. And they only provide limited information. If I tell you that Dave got a 50 on his stats in his calc exam, you'll think he did the same on both, but that's not the case. Even if I give you that additional information of, yeah, well, Dave did, well, the average on both those exams was 40, it still sounds like he did the same on both exams. And me telling you the standard deviations of 5 and 20, like, all that information is a little hard to parse. Sorry. So just telling you the raw scores doesn't tell you a lot. Which brings us to standard scores. We call these things standard scores, and that's just another name for z-scores, standardized scores, or I guess they're a type of standardized score. Because what we're doing is we're taking scores from two different distributions and placing them on the same scale so that we can directly compare them. Here we can't directly compare them because the distributions have different variability. So it's really hard to say, yeah, he got a 50 on both. That doesn't tell you the whole story, because you're comparing different types of tests. This one, everybody's on the calc, everybody's doing very differently. On stats, everybody's doing about the same, so it's less impressive to get a higher score in calc than in stats. But if I just tell you got a 50 and most people got a 40, that's not very informative. So what we're going to do is we're going to come up with a standardized score that creates a score where we can directly compare his performance in stats and calc across these two distributions. And we're going to incorporate how far away he is from the mean. So first, here's his score, 50. Is he above or below the mean? And we're going to get that by subtracting the mean from his score. And that will both tell us, is he above or below the mean by, is this number positive or negative? And it will tell us how far he is from the mean. The further the number is from 0, the further he is above or below the mean. And then we'll also account for variability by using the standard deviation. So I'm going to show you how this works. We're going to use this information to create a score, and we're going to create a formula that converts these scores of 50 on a distribution with a mean of 40 with a standard deviation of either 5 or 20 into scores that have the same mean and standard deviation, so now we can compare them directly. And what these standardized scores are, these z-scores, are going to do is they're going to allow us to use a single number that replaces that score of 50 that allows us to express how far above or below the mean Dave is. So here's the formula, or well, I'm going to show you the formula in a second. But yeah, these standardized scores are called z-scores. That's why this lecture is titled z-scores. And we can calculate a z-score for Dave. We could also calculate a z-score for all of his classmates if we wanted to. So here's the formula. It is X represents the score that you're looking at, whether that's Dave's score of a 50 or say his classmate Alia's score of like a 62 or whatever it is, minus the mean. So the mean of the set of scores, in this case 40, was the average score on this exam, divided by the standard deviation of the distribution. So if you're doing the stats one, that would be 5. If you're doing the calc one, that would be 20. Oh, yeah, and there's your notation. The score for a single person, the mean of your sample, and the standard deviation of your sample. And that's how you calculate a z-score. So you can do this for one person, you can do this for everybody. Now this part in red is very important because this is essentially the definition of what a z-score is. The z-score is telling you how far above or below the mean somebody is or a score is in units of standard deviation. If my z-score is 1, that means I am 1 standard deviation above the mean. If my z-score is -2, that means I'm 2 standard deviations below the mean. So let's calculate z-scores. I'm sorry, I'm going to sneeze. Sorry. All right, let's calculate z-scores for Dave in stats and calc. So let me get into a place where I can write again. Let me get rid of that. Get rid of this. Oh, I think I actually do need the notes there a little. There we go. Okay. So we're going to use this formula up in the upper right-hand corner. Now, I told you already that Dave got a score of 50. Right here. This red line is Dave's score of 50. Now we're going to do this in a universe where the mean on the statistics exam was 40, the mean in calculus was 60, and they both have a standard deviation of 10. So just eyeballing it, we can say that because the standard deviations are the same, it looks like Dave did better in stats than in calc, but let's check with the z-scores and see if they agree. Spoilers, they will. Sorry. Hopefully you weren't eagerly awaiting the answer. So first we plug in Dave's score of 50 minus the mean of the distribution. So I'm going to do it for statistics. We do need to do this twice, once for each distribution. The mean for statistics was 40 over the standard deviation of statistics right here, 10. 50 minus 40 gives us 10 divided by 10. Dave's z-score in statistics was 1. He was one standard deviation above he scored one standard deviation above the mean on his stats exam. Now we can do calculus. Dave still scored 50. We know that because of this. Minus the mean in calculus of 60. Divided by the standard deviation of calculus, 10. In this case, 50 minus 60 is negative 10, divided by 10. Dave's z-score in calculus is negative 1. In other words, in calculus, Dave scored one standard deviation below the mean. So comparing these scores, these z-scores, these standardized scores, they're now on the same scale. We can see just from these two numbers that, yeah, even though he got a 50 on both exams, relative to his classmates, relative to the other people who took the exam, he did better in stats than he did in calc, even though he got the same score. He was above average in stats, below average in calc. All right, yeah, and here I've animated all that out if you don't like my handwriting. In other words, yeah, Dave did better in statistics. He was above average in stats, below average in calc. Now, let's do this with the example with the different standard deviations, because I think this is where z-scores are mostly useful. Here, like I said, you could just eyeball that. Here, it's a bit harder to eyeball it. So let's do this again. Dave's score is still 50. The mean in stats is 40. The standard deviation in stats is 5. So 50 minus 40 is 10 divided by 5 gives us a standard deviation of positive 2. In statistics, Dave was 2 standard deviations above the mean, so he's pretty far above average. Now in calc, Dave still scored a 50. The mean in calc was still 40. But the standard deviation in calc is different than in stats. It's 20. So 50 minus 40 is still 10 over 20. 10 divided by 20 gives us a z-score of 0.5. In other words, in calc, Dave only scored half a standard deviation above the mean, as opposed to stats where he scored 2 standard deviations above the mean. So in both cases, he did better than the average student. But in statistics, he's probably in the top 97 or so percent of students. He's in the 97th percentile. He did better than 97 or so percent or so of his classmates. In calc, he's probably, I don't know, in the 55th percentile, maybe the 60th percentile, somewhere around there. So he's still doing better than average, but not nearly as better as he is in stats, if that makes sense. So there it is, animated all out, all nicely so you can read it. But yeah, in stats, there's only this small, let me draw this out. In stats, see this little bit here? This small sliver is the people who did better than him in stats. That's pretty small. In calc, this bit is the group of people who did better than him in calc. So a lot more people did better than him in calc than did in stats. That's what the z-score is essentially saying. Now, z-scores have 3 properties. The mean of a set of z-scores is always going to be 0. And I'd like you to take a second and ask yourself why this might be the case. Well, it's because half of z-scores are going to be above the mean, half are going to be below. 0 is always going to be the middle. We can also think of it like this. Let's say the mean of whatever we're looking at. Let's say we're looking at scores on the Beck depression inventory. I don't know how many points the BDI is. I think it's probably like out of 20. Question mark? I'm making this up. But it's a measure of depression. Let's say the mean depression score we get is 6. And then the population... Oh yeah, okay, 1 second. Let me try and say this again. Let's say the mean of the population, so the average score of people in the entire population of humanity, people who are depressed and not depressed on this is 6. Now let's say I get a score of 6. And let's say the standard deviation, this is population. Let's say the standard deviation of this is 2, I don't know. We can plug that into the z-score formula, where z is x minus m or x minus mu over the standard deviation. So this is the sample version. This is the population version. So I can plug in my score of 6 minus the population mean of 6. The population mean of 6 over the population standard deviation of 2. No matter what, if I score it exactly the mean, my z-score is going to be 0. The mean of a set of z-scores is always 0. When you convert scores into z-scores, the mean becomes 0 because you're subtracting the mean from the mean. It's always going to be 0. All right, now let's do standard deviation. This is the second principle. So first principle, the mean of a set of z-scores is always 0. Second, the standard deviation of a set of z-scores is always going to be 1. And I'd like you to take a minute and try and figure out why this might be the case. All right, let me draw this out for you. So first, the sort of plain language version is when you change each raw score into a z-score. So when you take your, say, raw score on an exam, I got 50 points out of 100, and I change that into a z-score, I divide the score by 1 standard deviation. So let's do this in the same way that I did before. Let's say we're on the BDI. The population mean is 6. I don't know if this is actually the case, by the way. I'm sorry if I'm wrong. And let's say I scored 1 standard deviation above the population mean. So let's say the standard deviation is still 2, and I score an 8. I'm 1 standard deviation above. Now, let's put that into the formula. My score is 8 minus the mean of 6 over the standard deviation of 2. 2 over 2, 1. Long story short, another way to explain this is that a z-score, the z-score is just how far you are from the mean in units of standard deviation. So 1 standard deviation is equal to 1 standard deviation. If I'm 1 standard deviation above the mean, then because z-scores are in units of standard deviation, I am 1 standard deviation above the mean. My z-score is 1. It's a bit weird to wrap your head around, but all you need to know is that the mean is always 0, the standard deviation is always 1. If you're 0 standard deviations from the mean, you're 0 standard deviations from the mean, and your z-score is 0. If you're 1 standard deviation from the mean, you're 1 standard deviation from the mean. Your z-score is 1, because that's what z-scores measure, how far you are away from the mean. All right. Oh yeah, there's your tip. Z-score is sometimes referred to as standardizing, as I was doing earlier in this lecture. This is because no matter what scale you're coming from, it always makes it so the mean is 0 and the standard deviation is 1. No matter what you're doing, whether you're comparing, say, I don't know why you would do this, but let's say I want to compare my height to reviews for the last movie that I watched. Height is on a scale of inches. Reviews for the last movie I watched might be on a scale of, 1 to 5 stars or whatever it is. Obviously, those are very different scales, but if I put them on z-scores, now both of their means are 0, both of their standard deviations are 1. No matter how different scales they started out on, by z-scoring, they are now on the same scale. They are now on a standard scale where you can directly compare them. That's why z-scores are so handy. No matter what you're doing, you can put things on the same scale and then just compare the numbers directly without having to worry about anything else. Now, those are the first two properties. First, your mean is always 0, your standard deviation is always 1. The final property of z-scores is that the distribution you have before you convert to z-scores will be the same shape as the distribution after. So there is a temptation to think that, oh, well, if I have a skewed distribution like this, negatively skewed, by the way, and I z-score it, it'll become a standard normal distribution. This is not the case. This is not how it works. If you have a skewed distribution and you z-score it, it's still going to be skewed. If you have a normal distribution and you z-score it, it's still going to be normal. No matter what, z-scores do not change the shape of your distribution. So the only thing that changes when you do z-scores about the distribution is the scaling is different. So let's say it looks like this one on the left is on a scale from, say, 0.4 to 1. On the right, it's been z-scored. Now it's a z-score of -6 to a z-score of +2. The shape of the distribution didn't change. The only thing that changed is the scores. Okay, there, as you can see. All right. Now here are 3 different distributions. I want you to take a moment and figure out which one of these 3 distributions has been z-scored. Yeah, it is distribution C. How do we know? Well, let me draw this out for you. First off, we know that the mean of, well, the first place to start is let's find the mean of these. These are all symmetrical unimodal distributions. They're normal distributions, so the mean is right in the middle. Now, the first thing that we know is that the mean of a set of z-scores is always 0. There are no zeros at all in the x-axis of graph A, so it can't possibly be A. There is a 0 for graph B, but it is not at the mean. On graph B, the mean is 2. The only answer is graph C. Graph C is a symmetrical unimodal distribution, which you can z-score other things too, but the mean is 0, therefore graph C is the only one that can possibly be z-scored, because z-scores always have a mean of 0. So there all they are on one slide. There's your 3 properties. The mean is always 0, the standard deviation is always 1, and the distribution, the frequency distribution of scores will stay the same before and after you standardize them. It will not change. Now let's say you have a z-score. It might be useful to convert it back into its original units, back into a raw score, sort of like uncooking something, I guess you could say. So here is the formula for a z-score. It is whatever score you're trying to convert minus the mean of that set of scores over the standard deviation. So what's the distance, and then divide it by standard deviation to turn it into standard deviation units, yada yada. You can convert this back. All you have to do, and actually I'm going to start on this slide, all you have to do is solve this formula for x. X is the original raw score. So let's say I know that my z-score is 2, my mean is 10, and my standard deviation equals 1. So I know that a z-score of 2 is equal to some number, x, minus 10 divided by 1. All I have to do to convert it back is solve for x. So I multiply both sides by 1. 2 times 1 is just 2, is equal to x minus 10. I should separate this out a bit more. And then I can add 10 to both sides. 2 plus 10 equals x. The original score that got me that z-score of 2 is 12. And we could just also just generally solve the formula for x. So if I have z is equal to x minus m over sd, then I can do z times the standard deviation is equal to x minus m, z times the standard deviation plus m equals x. And that's how you get this formula here. You're literally just solving the z-score formula for x, and that will allow you to convert z-scores back into their original units. Okay, so here's another example. And I'm just gonna dump down here. So let's solve for the raw score. I have a z-score of positive 2. So whatever this is, they scored 2 standard deviations above the mean. One standard deviation is equal to 7, and the mean was 69. So I can just plug this in. X is equal to 2 times 7 plus 69, which gets us 14 plus 69, which gets us, what is that, 83, I believe? I'm doing math in my head, which, as I've warned you, is not my strong suit. So let's see. I should have this animated out so that I can find out. Yeah, there we go. So you can convert a z-score back into a raw score as well. Now, there are some great advantages to z-scores that I've already kind of touched on a bit. The first is that they allow us to standardize different metrics. So let's say if I want to know if, say, my knowledge and stats are improving, I can take my z-score on a quiz and compare that to my z-score on a test to see if I've gotten better. Even though those might be on 2 totally different scales, say out of 10 and out of 100, if I z-score them, they're on the same scale, and now I can figure out, did I do better on the test or the quiz? And how's that working out for me? Am I improving, maybe? I could also compare my z-score on different measures of, say, depression or anxiety. So some measures might be on a scale of 1 to 7, some might be a 1 to 100, 1 to 20. Let's say I want to compare how I did on different measures. I can do that by converting to z-scores and then seeing, am I higher than most people on this one or on this one? Am I about the same on them both? I can do that even though they're on different scales. And going back to the example from the beginning, now we can say how well Dave did on his stats and calculus exam, even though those scores were coming from completely different distributions in different classes. So in example 1, he got that score of a z-score of positive 1 in stats and negative 1 in calc. He scored 1 standard deviation above the mean in stats. He was doing better than a lot of his classmates in stats, but he scored 1 below the mean in calc. He was doing worse than a lot of his classmates in calc. But z-scores aren't perfect. Nothing in this world is perfect, unfortunately. So there are some downsides to z-scores, and if you were wondering, well, why would I want to convert a raw score back into a z-score if z-scores are all great, here's where we get into why. So let's say I have 2 classes, 2 stats classes, which I do. I have a stats class this semester that I'm recording this at 9:30 a.m. and then one at 11 a.m. Even if I give people the same exam, let's say I have a student who's just like, I have a grad student or something test my stats exam. Even though they're taking the same exam, if I compare them to different classes, let's say the stats class 1 is an early morning one. Sometimes I teach an 8 a.m. stats class. And these people are very sleepy when they're taking their exam. And then the one on the right, stats class 2, is a more, like, say, later afternoon. They're a bit more awake when they're taking this exam. You might get different z-scores comparing your score to different distributions. You might score very well on a stats exam compared to a class where everybody's half asleep, but not score quite as well on that same stats exam compared to a class where everybody's awake. So you do have to take that into account. It can be a bit weird. The same score might get a different z-score on the same thing, just depending on who else you're comparing it to, depending which distribution or which sample of people you're looking at, which can get confusing. Another disadvantage of z-score, and I think the main reason you might want to compare it to raw scores, or convert it back to raw scores, is that if the raw score is meaningful, transforming it into a z-score hides that meaning. So let's say I am at some sort of theme park and I want to ride a roller coaster. And this roller coaster, you have to be, say, at least 5 feet tall to get on. Now, the sign that measures this is broken or something, so the attendant just says, okay, how tall are you? And I say, oh, well, my z-score for height is roughly negative 0.02, which I'm guessing that's roughly my personal z-score for height. So my z-score for height is negative 0.02. Can I ride? Who knows? Like, unless you have memorized the mean and standard deviation for height for a certain population, and then are capable of converting that in your head, like doing that math in your head, that is not useful information to you. I've just told you what I think is my personal z-score for height. You probably have no idea how tall I am right now, right? So let's say if I need to have some sort of information, like, okay, like, how many points do I need? How many questions do I need to get right on this exam to pass? Or how many? What does my GPA need to be to get into this program? Whatever it is, do our ratings need to be to get this season of this TV show renewed? If I give you a z-score, that information is probably not useful to you at all. It would be much more useful to just give you the original raw score. Your ratings need to be above, say, 76%. Your GPA needs to be above 3.0, whatever it is. So there are a lot of cases where z-scores can be useful, but also a lot of cases where it is much preferable to not use a z-score. So yeah, if I standardize the heights in this class, and I told you your z-score and height or something like that, that's not terribly useful. If I'm getting my driver's license and they want to say no, my weight or something like that, if I gave them my z-score, they would, like, look at me like, I don't know what look they'd give me, but they'd make me stand on a darn scale. It would be useless information for them. So in sum, z-scores are great because they can put all the scores on the same scale. They can also tell us how far and in what direction a score is from the mean. If your z-score is positive, that means the score is above the mean. If it's negative, that means it's below the mean. And the further your z-score is from 0, whether it's -2 or +6, the further it is from the mean. So it's telling you which direction and how far or how close. The mean of a set of z-scores is always 0. The standard deviation is always 1. This is pretty much the summary of the most important information, I think, outside of the formula. All right, before I get into, well, of course, if you have any questions, you can email me, but there is one more thing that I want to note that is potentially useful for your homework. One of the questions on your homework says, okay, it's something along the lines of, I'm going to make something up. You want to be a supermodel or something like that. Typically, supermodels, for whatever reason, tend to be tall. I don't know. So let's say you're applying to a thing, and whether this is right or wrong, I don't know. Probably it's not a great standard, but let's say they say you must be at least in the top 10% of height or something like that to be eligible to be at our agency or whatever it is. Top 10% of height of the people who apply for this. Now, let's say the mean height is, I don't know, 5'6" for people who are applying for this particular job. Your height is 5'8". Would you want a smaller or larger standard deviation if you want to have a chance of your height of 5'8" being in the top 10%? There's a homework question kind of like this. So you can't exactly change your height, so you have to kind of hope that the standard deviation is something certain. So if I have a very large standard deviation, say my standard deviation is a full 10 inches, that means that my height of 5'8" So let's see, 5'6". One standard deviation already is like 6'4" or something like that. So if I'm 5'8", I'm only right here with a standard deviation of 10. I'm only taller than, say, a little over 50% of the applicants. But with the same mean of 5'6", if the standard deviation is only 1 inch, then I am a full 2 standard deviations above the mean. And then I'm taller than something like 97% of the people applying. So in this case, a smaller standard deviation for the same score gives me a better chance of getting in. So let's say, in general, if you are applying to something and you want your score to be as high above the mean as possible or as low below the mean as possible, let's say you're in a race, you want to take as few seconds as possible, the smaller the standard deviation, the higher your score is relative to the other contestants. The lower the standard deviation, the less impressive your score is relative to the other people. So if you want to have a particularly high or a particularly low score compared to other people and the mean and your score are fixed, you want a smaller standard deviation. If you want a very typical score, where your mean and standard deviation are fixed, you want a bigger standard deviation. I don't know if that makes a lot of sense, but I think this should help you for the homework. With a smaller standard deviation, the same x-score will be further than from the mean. With the same standard deviation, with a bigger standard deviation, the same x-score will be closer to the mean, assuming the mean and the score don't change. Okay, I know that was weird, but yeah, I think that should help you on the homework. Okay, if you have any questions, feel free to send me or your TAs an email, and we'll get back to you as soon as we can. Thanks so much, and have a great day.